So Unit 4, chemical reactions, not yet at the quantities. Decomposition reactions have the general formula that one thing makes multiple things. You can have, and it doesn't matter, I just have A makes B and C, and B and C do not actually mean or represent any element on the periodic table specifically. They're just there for that general formula. Okay? It could even have additional letters. Okay? It could be X and plus Y. You could have one thing decomposing into multiple things. Okay? A decomposition reaction does not always just decompose into two things. Sometimes it can decompose into multitude of things, depending on what the reactant is. Okay? Depending on what the reactant is will depend on how many different things. Now, there are a few other things that are going to be the types of decomposition reactions. The two of these you will be asked to kind of predict the outcomes. They are the metal hydrogen carbonates and the metal carbonates. You will be asked to predict their products. Okay? The general decomposition reactions do not have a nice, neat, always gonna give you these products. So that's why we kind of mess with things a little bit. But the metal hydrogen carbonates and the metal carbonates always give us very predictable products. It's like saying 2 plus 3 is always going to give you 5. Okay? 5 can be decomposed into a lot of different things though, right? 4 plus 1, 2 plus 3. Right? And so you kind of just have to know what it is. Well, we're looking at it, these are going to be the always things. Metal hydrogen carbonates, when we look at these, it does not matter what the metal is. We have a metal, and then we have the hydrogen carbonate. Okay. I'm using calcium as our first example of a metal. I could use iron. I could use gold. Just not going to happen very often, but it could. Okay. They will always decompose into a metal carbonate H2O and carbon dioxide. A metal hydrogen carbonate will always decompose into a metal carbonate, water, and carbon dioxide. A metal carbonate will always decompose into a metal oxide and carbon dioxide. Now becomes a question, why not water? The general ones, the random ones, there is no general formula. Okay? The third type of decomposition reactions, there is no general formula. It comes from experience. Okay? That's why you just need to, the more chemistry you can see, the better. Now, it is this decomposition as to why every now and then I've seen them before. It was even on, like, I think an insurance commercial. So-and-so knew from an early age that baking soda on a grease fire is preferred. And you see the little baby throw the ball and it hits the baking soda that's above the stove. And it falls and hits and baking soda goes all over the grease fire. Every now and then, you'll see, I've seen service announcements. If you know anybody that is a fireman, they will also tell you, never, ever put water on a grease fire. Okay? Here's why. If you put water on a grease fire, it will decompose. Into hydrogen, which we have seen in the classroom goes boom, burns very hot, makes a fireball, and oxygen. Oxygen is fuel for a fire, isn't it? Because on your birthday, usually you just blow your candles out. Why? And there's more carbon dioxide on there. With a metal hydrogen carbonate, baking soda, which is a sodium hydrogen carbonate, you get a metal carbonate, water, very, very small amount, and carbon dioxide. Well, this metal carbonate that you put on the fire, the baking soda, just further decomposes into a metal oxide, and sodium oxide is basically an inert solid. Doesn't burn, just kind of sits there. Boring, right? And more carbon dioxide. So when you have a grease fire, covering it is one thing. Unfortunately, though, that can add some flash, because if you lift it up and it just reignites and goes right in your face. If you put water on it, very bad things can happen. Extremely dangerous. Very bad burns. Because it's like basically a fireball will come back at your face. And people have been severely burned by it. Okay? Baking soda. Okay? Because it decomposes to make carbon dioxide and an inert solid. Very little water is given off, but again, that metal carbonate that is over here just further decomposes, making a lot more carbon dioxide than what water is produced. That's what it is, the safest thing to do. So, let us try it out. Sodium hydrogen carbonate decomposes into something we should know. always going to decompose into H2O, technically gas, and carbon dioxide, gas. Now, what usually happens, a lot of times students forget, and they will just say, and sodium. That would not be good, cool as it may be, because sodium metal would be a really fun way to make that, okay? Because then you could do it at home, right? But that's not the product. There's something else there. The previous slide, what was the other part? It was a metal. It's a metal carbonate. Now, here's the thing. This is usually what people write. And there's nothing wrong with that, except for the fact that it's wrong. Can we see why it's wrong? Not the fact that it technically is a solid. Let us take a little closer look. Move that off to the side a little bit. This is a very common thing students forget. We just think they all match up, right? If we look on our periodic table, we will see that the charge on sodium is a +1. Charge on carbonate is a -2. With that, we can see charges don't match up, and therefore we need to crisscross. It is this little thing that makes that go there. Now, if I didn't, I'm going to fill out my chart here real quickly. Okay, reactants and products. I'm going to put my sodium, my hydrogen, my carbon, and oxygen because it's decomposes, so it all goes on the other side. If I did not put that 2 there, it would look like this. And 3 and 6. It would look like that. And you get very, very frustrated really fast. Because you put a 2 in front of that sodium hydrogen carbonate that it would take to balance it, but then all of a sudden you got to put a 2 on the other sodium. And that changes the amount of carbon. And then you got to change a whole bunch of stuff, and you're going to get really frustrated really fast. So here becomes another one of those lessons, those little hints about balancing. If you are balancing and it is not working, and it is just not working at all, double check your charges. Make sure that they are what they're supposed to be. Because if we write the right one in, now it looks really easy to balance, and it is. Now all I have to do is not a 3. That's not right. I need to put a 2 there. Okay? Those charges are going to be the thing that a lot of students get. Okay? I bring this up not to scare you, but to warn you. Pay attention to your charges. They matter. Okay? Let's look at the next one. We're going to need this a number of times, so I'll make it again here. Iron 3 hydrogen carbonate. It also can go by the name of iron 3 bicarbonate. Is going to give me water, carbon dioxide, I'll give it a gas, and if you get at this point, you're like, ooh, it's an iron 3. So maybe I should check on those charges. So kind of off to the side a little bit. And here's the thing, the oxidation state's never going to change. You know you need a metal carbonate. And now you're like, oh, those don't match up. We crisscross. And things, so we get iron 3 carbonate. And technically it's a solid. Now we start filling it out. We have our iron. We have our hydrogen. We have our carbon and our oxygen. When I look at this one, you can see I got my iron 2. Because I have it split up, everything inside that parentheses, that 3 gets distributed. Ooh, math term. Distributed inside. So it'll be 3 hydrogen, 3 carbon, 9 oxygen. So we go 3, 3, 9er. Then on the other side, hydrogen goes to 2. Carbon gets a little funky as we go 1 there plus 3 is 4. It starts looking like a hot mess. Oxygen, 1 plus 2 is 3 plus 9. Whew. 3 plus 9 is 12. Whoo, Lordy. Looks like a lot of fun. Well, we only really have, because of this, the nature of the fact that it's a decomposition reaction, we might be reluctant to make any major massive changes. By putting a 2 here, I'm changing a whole bunch of stuff, right? And so that becomes, but we want to change the reactants as little as possible. Okay? Now everything we change, we want to change as little as possible. And so now I have to be careful. I'm going to take on carbon first. Why? Carbon's in 2 places. Some people are like, well, why wouldn't you take on oxygen first? Oxygen looks like a hot mess. We're just going to leave that alone for a while, okay? We don't want to deal with that quite yet. Maybe it'll all figure itself out. Okay? It's like a bad hair day. Sometimes you just let it leave it alone and just pray for wind. Okay? Well, I got 3, so maybe I can ask myself, I need 6. What plus 3 gives me 6? 3 gives me 6. Okay. And I just have 1 on my carbon dioxide, so if I put a 3 there, now I have 6. But some people are like, yeah, but that oxygen. And I'm like, yeah, just keep track of it. Just keep track of it. Okay? 1 plus 6 is 7 plus 9. 9 plus 7 is 16. So it's getting closer, right? Hydrogen doesn't look too bad, right? Put a 3 there, because 3 times 2 is 6. You're like, okay, I like what you're doing here, Peterson. And then let's look at our oxygen again. That was the last thing we do. Okay. 3 plus 6 is 9. Plus 9 is 18. Well, that hot mess just turned around and looks pretty darn nice now. Just sometimes leaving it alone instead of being like, all right, that's where the problem's at. Let's just run at it full steam. Yeah, sometimes you're just like, you know what, that's a bad hair day. Let's just hope for some wind. It'll just blow it around a little bit and just make it look nice. And everybody's having a bad hair day. Woohoo! Okay. So sometimes they just have a way of working themselves out, and you're like, oh, it might seem daunting at the first, but you have to just kind of just take your time, work it out. Now the next one, we have a metal carbonate. So here, water can't be an outcome. There's no water, there's no hydrogen present. Carbon dioxide can be there. And here's what, well, it's going to be a gas. And sodium oxide. My charges don't match up. Glorious. Na. O. They don't match up. So we got to put that 2 there. Now we have it to match up. And the other thing is, because I paid attention to my charges, what also just randomly works out? It's balanced as it's written. Yeehaw! All right. Now, we move on, and we have our iron 3 carbonate decomposing into iron 3 oxide, better known as rust, and carbon dioxide. Now I can see from this one, it is definitely not balanced because my carbons are not. So I will fill out my little chart. Irons look good. Carbons look bad. Oxygens, well, it's what oxygens do, and they just look weird. So we start fiddling around. Got to start with my carbon because that's the thing that's throwing me off. Put a 3 there to make my life easy. Okay. 6 plus 3 is 9. Well, that isn't that bad, I guess. Wasn't that bad. And the last one, chromium nitrate. Most nitrates will decompose in this manner. That's why some nitrates are a little bit scary to keep around. Chromates as well, they're oxidizers. You can see that we got some things going on that just don't work. Or if you can't see, we write it out so that we can see. Cr, N, and O. Chromium 3 is 1 and 1. Nitrogen goes 3 and 3. Oxygen goes 9er. And 6 plus, ooh, that's just weird. 6 plus 2 is 8. Man, wouldn't it be really nice if we could do this? Or maybe just, yeah, we want a 1.5 that. Wouldn't that be really nice? Can we have halvesies? No, we can't. However, if it would be really nice of us to have those halvesies, that means if I just double everything, guess what? It works out. So that's where we can use a half to help us make our lives easier in balancing. So sometimes those halvesies, even though we can't use them, if we recognize like, hey, if I put a 1.5 here, it would be nice. Or if I put a 3.5 here, it would be really nice. But I can't. But what I can do is multiply everything by 2 to get rid of the half, and it works out. That's why sometimes leaving oxygen last is really nice and helpful.